In this video, I will discuss sampling distribution about the mean. A sampling distribution is the distribution of all of the possible values of a sample statistic for a given sample size selected from a population. For example, suppose you sample 50 students from your college regarding their mean GPA. If you obtain many different samples of size 50, you will compute a different mean for each sample. We are interested in the distribution of all potential mean GPAs we might calculate for samples of 50 students. Different samples of the sample size from the same population will yield different sample means. A measure of variability in the mean from sample to sample is given by the standard error of the mean. So it will be calculated as the standard deviation divided by the square root of your sample size. Note that the standard error of the mean decreases as the sample size increases. If a population is normal with mean mu and standard deviation sigma, the sampling distribution of the sample mean is also normally distributed with the mean of mu and a standard deviation of sigma over the square root of n. So as you can see, if it comes from a normal population, the normal sample distribution will both have the same mean, but as you can see, the sampling distribution will have a smaller variability. The graph is more narrow than the normal population distribution. So what happens if your population is not normal? We can apply the central limit theorem. Even if the population is not normal, sample means from the population will be approximately normal as long as the sample size is large enough. So how large is large? So for most distribution, your sample size has to be greater than 30. And this will give a sampling distribution that is nearly normal. For fairly symmetric distributions, your sample size has to be greater than 15. And for a normal population distribution, the sampling distribution of the mean is always normally distributed. So as you can see, as the sample size gets larger, the sampling distribution of the sample mean becomes almost normal regardless of the shape of the population. So let's go through an example. Suppose the wait time to be seated at a restaurant has a mean of 8 minutes and a standard deviation of 3 minutes. A random sample of size n equal to 36 is selected. What is the probability that the sample mean is between 7.8 and 8.2? So even if the population is not normally distributed, we can use the central limit theorem because our sample size is greater than 30. As you can see, our sample size is 36. So the sampling distribution of the sample mean is approximately normal with a mean of 8 minutes, and your standard deviation will be 3 divided by your square root of the sample size. So it's 3 divided by the square root of 36. This gives me 0.5. Now, we talked about normal distribution previously, and you can use the z-table if you want. You just have to standardize your value. So you're going to take x bar minus the mean divided by sigma all over the square root of n. So that's if you wish to use the table. So we're going to go through this problem. I'm not going to go through it with the table because I've already gone over that, but I will show you how to do it with technology, which is the same way we did normal distribution before. So if you wish to use the table, once again, you have to standardize both of your values because we're looking at numbers between 7.8 and 8.2. Okay, so that was the question. What is the probability that the sample mean is between 7.8 and 8.2? So you can go ahead and standardize your values. As you can see, you get z is between negative 0.4 and a negative 0.4 and a positive 0.4. And then you will go to your table and find that probability and get the answer. Okay? But I'm going to use it with technology. So with technology, I don't have to standardize. The technology would do it for me. So I'm just going to redraw this picture. Okay? And we want this area in between here. Okay? We already know that the mean, they told us the mean is and the standard deviation is 0.5. So this is 8, and the standard deviation, once we calculate it, is 0.5. So let's go ahead and do this in StatCrunch. So in StatCrunch, I'll go to Calculators, Normal, and I want to do Between. Okay, because if you look up here, you have Standard, but the ones we have is X bar is in between those two values. So we know the mean is 8. Standard deviation is 0.5. We were looking at, let me go back, I forgot already, 7.8 and 8.2. And 8.2. Okay, we hit compute, and there's our answer, 0.3108. And it gives you the visual, the shaded area in between those two values. And that's the same answer that we get if you standardize your values and use the table, 0.3108. We can also use my normal distribution Excel template. So in this one, we're going to put in the mean and the standard deviation, but this time we have a lower and upper bound. So my lower bound is 7.8 and my upper bound was 8.2. And we want this answer here, oops, where it says 0.3108. X is in between the lower and upper bounds. Let's look at another example. The amount of water in a 2-liter bottle is approximately normal distributed, with a mean of 2.05 liters with a standard deviation of 0.025 liter. What is the probability that an individual bottle contains less than 2.03 liters? Okay, so I'm not going to go through and standardize any values. I'm just going to go ahead and have technology do it. So I always like to draw a visual when I do normal distribution. They told us that the mean is 2.05. We want to find the probability that it's less than 2.03. That was the question. But if you look at this problem, it's only looking at an individual bottle. It's not looking at a sample mean. You didn't take a sample and calculate the sample mean. That's not what this is. This is the individual bottle. So this is just like the normal distribution problems you did previously. So we know our mean is 2.5. And we know the standard deviation is 0.025. So I'm just going to go ahead and plug this into StatCrunch. This is a standard one. So the mean is 2.05. Standard deviation is 0.025. We want everything less than 2.03. And we want to make sure we have the less than, not greater than. And when we hit compute, we get 0.211, I'll round it up, 0.2119. And that's the visual that I have on the slide. So this is 0.2119. We can also go ahead and do it in my Excel template. 2.05. This is 0.025. We don't have a lower and upper bound. We just have an X value, and that X value is 2.03. But we want it for less than, so we want this here, 0.21186. Once again, you can round to 0.2119. So looking at this same problem, what if you drew a sample of 25 bottles? What is the probability that the sample mean is less than 2.03? So this time we're not looking at an individual bottle. We're looking at a sample of 25 bottles. And we want to know the probability that the sample mean. So basically we're calculating this. Okay. So if that's the case, our mean for this sample is 2.05. Our standard deviation we're going to have to calculate as 0.025 divided by the square root of our sample size, which is 25. Okay. When I calculate that out, I get 0.005. So these are the numbers that I'm going to input along with the 2.3. So this is 2.03 here. Once again, we're still looking at the same shaded area. We just have a different standard deviation. So let's go ahead and plug this into StatCrunch. But this time, like I said, we have different values. We're going to plug our standard deviation in to be 0.005. Hit compute, and it's a really small number. It's 0.00003. So that's pretty much 0%. All right, so we'll say that this is 0. It's so small, it's just 0. Okay, if we do it into my Excel template, the only thing we need to change is the standard deviation, 0.005. As you can see, we get this small number. When you see that E, negative 0.5, that means you move your decimal over 5 places to the left. Once again, a very small number. So what does this mean? There is a 21.19% chance that an individual water bottle will contain less than 2.03 liters. But there is a 0 chance that the mean amount of water in 25 water bottles would be less than 2.03 liters. Okay, that's the end of this video.